Welcome back to our Algebra 2 series. Today we are up to section 3.1 where we will be looking at functions and domain and range. In the past we've looked at ordered pairs. Usually it refers to an xy coordinate. For example, 1, 1 here is an ordered pair. But what if we had a set of ordered pairs like this? A relation is a set of ordered pairs, just like this. If we're being picky, a relation should have squiggly brackets on either end of it, like this. The domain of a relation is the set of first coordinates. So in this case, the domain of this relation is 1, 2, 3, and 4. The range of a relation is a set of second coordinates. So the range would be 1, 4, 9, and 16. Domain and range do not need to apply to only numbers. For example, we have some magic cards: Badlands, Fork, Jump, and Manifold, all from Revised. And then we can assign a value to each one. Badlands is $388, Fork is $45, Jump is $1, and Manifold is also $45. In this case, the domain would be Badlands, Fork, Jump, and Manifold. The range would be $1, $45, and $388. Now you may notice we have two cards that are worth $45. We don't repeat values in the range. So because 45 shows up twice, we only need to list it once in the range. So let's rewrite it this way as a list. The domain as one list and the range as another list. Notice that for each card, there's exactly one value assigned to it. This is a special kind of relation called a function. A function is a relation that assigns to each member of the domain exactly one member of the range. You can think of it as an input and an output. For every input you put in, you only get out one output. Another way to look at it is with arrows. Badlands points to its output of 388, Fork points to its output of 45, Jump points to its output of 1, and Manifold points to its output of 45. So let's do another example with four names here: Julie, Rustin, Sarah, and Matt. This will be our domain. Our range will be height. How tall is each person in centimeters? So let's draw some arrows. Does anything stand out as looking odd to you? In this case, the input name of Julie provides two outputs. This is saying that Julie is two different heights at the same time, which isn't really reasonable. Remember, a function is a relation that assigns to each member of the domain exactly one member of the range. So this is not a function. We do have a domain and a range, but because of this relationship between Julie and two heights, it is not a function. You can think of a function as a factory with inputs and outputs. Typically in algebra, the input is a variable, like x. We typically refer to the function like this, with an f and x following it in parentheses. We would read this as f of x. This is shorthand for the function of x. It's a function that's dependent on the input that is x. So let's say that f of x is equal to x plus 3. We can ask ourselves what happens with different inputs. So what is f of 1? Well, we replace the x in the function with that input of 1. So f of 1 is equal to 1 plus 3. So f of 1 is 4. Just like f of 7 would be 10 because we add 3 to the input, and f of 99 would be 102, again, because we're adding 3 to the input to get the output. We could summarize this function like this, with three ordered pairs, surrounded by the squiggly brackets. Let's jump over the whiteboard and do some examples. Now, how does this happen every year? You put them away nice, and every year you're left with something like this. Okay, we're going to go up here and create a relation with some terrible squiggly brackets. 4, 1 is an ordered pair. 7, 1, followed by -2, 4, and 1, 1, and a squiggly bracket. So the question is, what is the domain and range of this relation? So the domain, well, it's the first number in each ordered pair. So the domain would be 4, 7, -2, and 1. It's the first number in each ordered pair. So the range is the second one. So it's 1, 1 again, so we don't need to write it again, 4, and 1 again. So that's it. The range only has 2 values in it. Now I'm going to add one more value to this relation. So we've added a 7, which we already have in the domain. We've added another range, so that would be like this. So the question is this a function? Is there a unique output for every input? So let's do a little table here. We're going to do D and R like we did before. So the domain is 4, 7, -2, and 1, and the range is 1, 4, and 3. So let's look at each ordered pair. 4 goes to 1. 4 goes to 1. Okay. 7 goes to 1. We're allowed to do that. 2 domains can point to the same range. -2 goes to 4. Okay, that's fine. 1 goes to 1. Okay, that's still fine. Now 7 goes to 3. 7 goes to 3. Well, now that's a problem. For each input, we need to have exactly one output that corresponds to it. 4 can go to 1, and 7 can go to 1. That's fine. The problem is that 7 is going to 1 and to 3. You can't have one input and 2 outputs. So once we added this ordered pair here, this is no longer a function. Oops, forgot our brackets. So this is no longer a function. Before it was, but once we added this and added this second output for 7, this is no longer a function. All right, let's clean this off and do another example. Now I'm going to write something kind of weird up here. I'm going to write g of s. So what does that mean? It doesn't mean junction. We can name functions whatever we want. So we can have f of x. That's a function that's using x as an input. But we can substitute any variable for the name. So this is just another function. It's just g. And the variable that it's dependent on is s. So this will make a little more sense once I write it out. That g of s is 2s plus 4. So the input is s, and the output of this function, you have to multiply it by 2 and add 4 to it. Again, we can think of it as, a little factory, right? And the name of that factory is g of s. And what it does is it doubles the input and then adds 4. So here's the input, here's the output. So the input would be s, and the output would be, our range values, the things we get. And we can maybe add a little, smokestacks for pollution or whatever. So I want to find some outputs. So we're going to find g of 1, g of -7, and we'll say just g of 5 equals. So g of 1, and we're just going to spell it out here. We replace s with our input. So this would be 2 times 1 plus 4. So that's 2 plus 4 is 6. G of -7 is, again, 2 times -7 plus 4. So -14 plus 4, this would be 10. And g of 5, again, we're just rewriting this with 5 instead of the s. So 2 times 5 plus 4. 2 times 5 is 10, plus 4 is 14. I'm going to write another function down here, p of x. Again, just using a capital P as a different name. It's still a function, but this time x is a variable again, as our input. And this function wants 3x squared minus 2x plus 5. And let's find p of 0, p of 1, and p of negative 2. Okay. So 3 times 0, well, let's just write it out. 3 times 0 squared minus 2 times 0 plus 5. So all I've done is taken this equation, substituted in 0 for the x's. So 3 times 0, that's 0, minus 0 plus 5. This ends up being 5. 1 is going to be 3 equals times 1 squared minus 2 times 1 plus 5. So 3 times 1 is 3, minus 2 is 1 plus 5, so it ends up being 6. Alright, so this might be a fancier one. Do we have room to squeeze this in? We need to place. Let's just do it over here, maybe. This might be a little bit more math. So it's going to be negative 2, 3 times negative 2 squared minus 2 times negative 2 plus 5 equals. So negative 2 squared is 4. 3 times 4 is 12. Let's do it one term at a time. 2 times negative 2 is negative 4, but we're subtracting it, so we're really adding 4 and adding 5. Let's just make sure I did that right. P of negative 2 is 3 times negative 2 squared, 3 times negative 2 squared, minus 2 times negative 2 plus 5. Negative 2 squared is 4, 3 times 4 is 12, negative 2 times 2 is negative 4, plus, we switch our signs, it's positive. Okay, so this equals 21. All right, let's clean this off and do one more example. All right, we're going to do h of t. Again, just a different name, and the variable here now is t. What I want to find out is the absolute value of t minus 2, where we want to find h of 3, h of 93, and h of negative 100. And we'll just kind of put all our equals out here. So all we need to do is substitute this back into the equation. So what is the absolute value of 3? Actually, no, we're just going to write it all out. Absolute value of 3 minus 2. This is going to be the absolute value of 93 minus 2, and the absolute value of negative 100 minus 2. So this is 3 minus 2. This is 93 minus 2. And again, the absolute value of this negative 100 is going to be 100 minus 2. So now we can do all our math. 3 minus 2 is 1. 93 minus 2 is 91. And 100 minus 2 is 98. That's it for today. It's a pretty short section. We'll see you next time.